Lesson 10. Biot-Savart Law, Ampere's Law. Section 10.2. Ampere's Law. Suppose there are line currents I1, I2, and I3 in space, and a closed path CP. H1 and H2 are the magnetic field strengths at points P1 and P2 on the closed path CP respectively. The dLs are differential vectors tangent to CP. The inner product of H and dl is a differential component of H, that is tangent to CP. According to Ampere's law, the line integral of H along the closed path CP equals the current enclosed by CP. In this case, it is I1 plus I2 plus I3. In section 3.3, we learned about the conservative property of electric field intensity E, as expressed by this equation. The line integral of E along any closed path is 0. The magnetic field is not conservative, if a current exists in space. If the currents are distributed with a density of J amperes per square meter, then the right-hand side of Ampere's law becomes a surface integral of differential current density J ds on the surface S, which is encircled by the closed path CP. Exercise 10.2.1. Pause the video, and answer the problem. Find the magnetic field strength H. The answer to exercise 10.2.1. You can select a circle with a radius of r meters, centered on the infinite conductor, as the closed path CP for the line integral of H. We can use Ampere's law. Due to the symmetry, H is tangential and has the same magnitude at each point on CP. The line integral along the circumference with radius r is obtained by this equation. This is the answer. Since the vector H is tangential to the circle, the cylindrical coordinate system is convenient for expressing H in this direction. The unit vector AZ is along the z-axis, and the infinite current line lies on this axis. AR is the unit vector in the radial direction from the z-axis. A phi is the unit vector perpendicular to AR and tangent to the unit circle. The magnetic field strength H, at a distance of r meters from an infinite line current, can be expressed using the unit vector A phi. Exercise 10.2.2. Pause the video and answer the problem. Show that the magnetic field strength H is expressed by these equations. The answer to exercise 10.2.2. When R is equal to or greater than A, the closed path CP can be set as shown in this figure. The current J flows only in the area pi a squared. H is obtained as shown in this equation. When R is equal to or less than A, the closed path CP can be chosen as shown in this figure. Due to the symmetry, we can conclude based on Ampere's law that only the current inside CP contributes to H. This is the answer. Exercise 10.2.3. Pause the video, and answer the problem. Show the magnetic field strength H at point P. The answer to exercise 10.2.3. The closed path CP can be defined as shown in this figure. Ampere's law provides this equation, where S represents the surface enclosed by CP. For the width L, the right-hand side is given by JL amperes. CP can be decomposed into 4 straight paths from CP1 to CP4. For the symmetry of the current distribution, the y components of H are 0 on CP2 and CP4. On CP1 and CP3, the directions of the x components of H are opposite to each other. The differential line elements are shown in this figure. Then the line integral results in this relationship. If R1 equals R2, due to the symmetry, we obtain this result. Note that, when R1 equals R2, it can be observed that the result is independent of the specific values of R1 and R2. Therefore, this result holds for any R1 and R2. And this is the answer to exercise 10.2.3. Exercise 10.2.4. This is your homework. Pause the video, and answer the problem. This is a brief summary. In this lesson, we learned about Ampere's law. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.